Here we go. Station WMTH, the station that rocks the docks and reaches the beaches. It's almost springtime. Woohoo! Yeah. Let's get going. We're going to work with complex numbers in polar form. So we've played around with complex numbers before. Hopefully, you must have to get here. And they would look like this: -1 plus I, or 9 squared root of 3 plus 9i. There's two parts to a complex number. There's the real part and there's the imaginary part. So there's your real part and there's your imaginary part. In general, they're written in the form of a plus b times I. Now that's in kind of what it's called rectangular form. The same form that we had with Descartes. Descartes regarded numbers as being ordered pairs, or points on the plane as being ordered pairs. But with complex numbers, just like regular numbers and points on the plane, you can regard these things as being a little bit different. We can regard them in polar form. So instead of specifying, for instance, -1 plus I, -1 being along the real axis, and then your imaginary axis is here, -1 plus 1i, that's that point there. We can also specify two different things, and you might be familiar with these things: r and theta. And in so doing, instead of writing it in rectangular form, we're going to write it in polar form, which is down here. R times cosine of theta plus I times the sine of theta. So that's polar form, and that's what we're going to work towards. So there's two things I need to know from this graph in order to convert this point to a point in polar. I need to know R and I need to know theta. So let's set about finding out those two values. Here and here. Well, you know the length of each of these sides. The length of this side is 1, although I'll write a -1. The length of that side is 1. Can anyone tell me what R must equal? Not 2. Not 1 either. Not the square root of 1. We're 0 for 3. Kind of like my favorite basketball team against their rivals, but hate that. Yeah, square root of 2, right? This squared plus this squared, well, that's 1 plus 1 is 2, square root of 2. So that's what R is. Now, in this particular case, we could do a lot of fancy things to find what theta is, but can you just look at theta and know what theta is? Are you that comfortable with your trig yet? Not 120. Yeah, these two angles have to be the same. This has to be a 45-degree angle, and this has to be a 45-degree angle, right? So 90 plus 45 gives me 135. So hopefully you get comfortable realizing that when you have an angle that bisects a quadrant, it's going to be a multiple of 45. So 45, 135, 225, or 315, depending on what quadrant you're in. Now, if you're not comfortable with that, if you're like, I'm not good with that, one good way to do this would be the cosine. What's the cosine of theta? Wow, come on. It's supposed to make me look good here, right? All right, -1 over the square root of 2, which is -√2 over 2. What angle has a cosine of -√2 over 2 in the second quadrant? 135. So this point, -1 plus I, could also be rewritten as the square root of 2 times cosine of theta, so cosine of 135, plus I times the sine of 135. And that's it. So we've changed the form of our complex number into polar form. And this form of a complex number has some advantages. And we'll go over those advantages in a little bit. But right now, let me see if there's any concern on how I got something or I wasn't clear on any of this someplace. Looking good with this first one? Let's try another one then. Let's try this one. 9 square roots of 3 plus 9i. So again, you've got a real axis. And that's where you're going to draw 9 times the square root of 3. And then your imaginary axis is up here. Your imaginary axis is really taking the place of the y-axis, right? And we've got a distance of 9 up here. So, okay. There's two things that I need to know. I need to know theta, and I need to know r. Let's start with the easy part. Let's start with r. What am I going to do to get r? I shouldn't have dead silence here. Come on. Help me out. Vivek? We're not going to use sine or cosine of those yet until we find out what r is. Alton? Any idea how to find r? Well, let me try. That's a 9. Yeah. Let me try and be a little bit more explicit here. This side and this side right here. It's 9 times the square root of 3, right? It comes from this right here, there, and there. Keep in mind what we have is the length of these sides. This is 9 times the square root of 3, and this is a height of 9. There's your real part. There's your imaginary height. So, okay. Looking good there. If you're trying to find the radius, yeah, absolutely. Use the Pythagorean Theorem, right? So, it's going to look like this. Square root of 9 square roots of 3 squared plus 9 squared gives me 81 times 3 plus 81. That's going to be the square root of 324. The square root of 324 is 18. So, hey, looking good there. We've got all three sides. Daryl, I need to find theta. And looking at these three sides, I'm deciding that I want to work with this side and this side because these are nice and easy. I don't want to have to type in the square root of 3 into my calculator. What trigonometric formula involves this angle, this side, and this side? Perfect. Sine of theta equals 9 over 18, which means sine of theta is 1/2. What's that tell us about theta? Yeah, inverse sine of 1/2 is 30 degrees. Pi over 6 if you're talking in radians, but 30 degrees is fine. Not worried about radians versus degrees at the moment. So we needed two things. We needed r and we needed theta. Are we okay with both of those? All right, thank you. So let's put it into r cis theta form. That is this form right here. Your final answer should be, let's see, 18. Let's see, where do I have room to write that? I guess I'll just squeeze it in here. 18 times the cosine of 30 plus I times the sine of 30, like that. So there's your answer. That's converting it from rectangular form, where we started out, right here, down to this over here. Would it be worthwhile to double check this and make sure that that actually works, that this is actually equal to that? Maybe it wouldn't be bad. In fact, we're going to do two problems like that. But we'll start out with this one right here. Let's see that this and this are actually the same thing. So let me start out with 18 times a cosine of 30 plus I times a sine of 30. And let's fill in a few numbers. What's the cosine of 30 degrees? Root 3 over 2. Good. Root 3 over 2 plus I times the sine of 30. Ivana, what's the sine of 30? All right, so 1/2. Cool. And last but not least, it's distribute. It's going to be 18 times the square root of 3 over 2 plus 18 times I times 1/2. But the 2's are going to cancel, right? 9 square roots of 3 plus 9i. And we're back to where we started from. So even though it might look like kind of a funny way to write this, it is equivalent to what we started out with. It's this latter way, or the polar form, that actually gives us certain advantages in terms of doing different calculations, especially when you're calculating roots. Are we okay with this one? Okay, I think it was problem number 20. Let's try another one kind of like that, that is checking things or putting things back into rectangular form. Are you pretty much okay with that one? Because I have another one in mind that I'd like to do. And it's not going to work out nice and even, but that's okay. It's problem number 34. Three times cosine of pi over 10 plus I times the sine of pi over 10. And I want to write that in the form of a plus bi, and we're going to round that to the nearest thousandth, for instance. So if I distribute that 3, I'll get 3 cosine of pi over 10 plus 3i times the sine of pi over 10. And I'm thinking we need to break out the calculator on this one. They don't happen to have pi over 10 memorized. It's an 18-degree angle, if you're curious. If I'm going to calculate this thing directly, there's one thing I need to make sure of when I plug it into my calculator. What is it? Yeah, you want to make sure that you're in radians. So let's see here. Yeah, this one happens to be in degrees. So I'll first change the mode, go down to radians, and I want 3 cosine of pi over 10. So 3 cosine pi divided by 10, 2.8531, etc. Now, typically speaking, if I asked you to round to a particular number, then there's a point of credit to rounding to that number. So please be careful in rounding. This is going to be approximately 2.853. Let's do the same thing with the sine. 3 sine of pi divided by 10. And actually, not like that. I'll do it like this. Plus 0.927 times I. Don't forget the I, because this is a complex number. All right, I got a little... For a second, I was going to write it as an ordered pair, but it's not an ordered pair. How are we looking on 34? Is that one all right? So make sure you can go back and forth between complex and polar. Let's keep going on our handout, though, unless there's some more thoughts on 34. Am I good there, Amanda? Yeah, that's all all that they're asking you to do, is write it in the form of a plus bi. So, so-called rectangular form. Now, part of the beauty of this kind of thing is right down here. So, good question. Why put things in polar form? Well, one of the things you can do quite easily when things are in polar form is multiply numbers. So I've got two numbers in polar form, one here and one here. When I multiply numbers in polar form, then all that you have to do is multiply the radii, that is R1 times R2, and add the angles. So there you go. So you multiply the radii and add the angles. Likewise for division, let's see, there we go. Likewise for division, you're going to divide the radii and subtract the angles. So it's kind of nice that you can do things like this. So we'll practice it with a couple problems, starting with number 38. Actually, you know what? We can do this one down here. I think this is 38, though. Let me double check. 80 and 200. Yes, this is 38. So the first part of this is to calculate z times w. So z times w, you're already starting out with your numbers in polar form, so it's going to be 2 times 6. So 2 times, does it help out if I keep them kind of color coordinated? Is that? All right. 2 times 6 times the cosine of 80 plus what? 200 plus I times the sine of 80 plus 200. In other words, 12 times the cosine of 280 plus I times the sine of 280. And that's nice. What it avoids is having to FOIL things out. It's pretty quick and actually pretty simple. We kind of have to leave it here unless you wanted to convert to rectangular coordinates. There's not much more we can do. This and this aren't like terms. We can't combine these in any ways because this is a real number and that's a complex number. So there's really not much we can do. They're not like terms. How are we with that first one on 38? Not bad. Can you try the second part to divide these things? Make sure you do it in the proper order. Z divided by W. Okay, so this one actually works out okay. So you're going to divide the radii. So that's this r here is really the distance that this is away from the origin. So there's an infinite number of points on the circle of that radius. But we're specifying that one that has an angle of particular angle of theta. Here our radius is 1/3 times a cosine of minus 200. How about minus 120? Yeah, minus 120 looks a little bit better. So minus 120 plus I times a sine. Now here's a little trick for you. This angle and this angle have to be the same. So or plus I times a sine of negative 120. This is probably the only time that I'm not going to ask you to use your even-odd properties. I'm not worried about you factoring this one out. And this one would just disappear, right? Because cosine is an even function. So we can leave it like that. You can actually figure out a little bit more here. In this particular one, cosine of 120 would be, let's see, 1/2, negative 1/2. Yeah, negative 1/2 plus sine of 120 would be negative root 3 over 2. Is that right? Let's see, it'd be 240. Yeah, 240. Yes, negative root 3 over 2. And then you can distribute the 3. I'm not so much concerned about that as I am this part right here. I just want you to simplify it as I have on the bottom of this page right here. Yeah, there should be an I there. Thank you. I. Yep. But this is what we're looking for. That was the goal of this particular problem. So we're okay on that one. So multiplication, I mean, look, I usually put a problem or two like this on an exam, but they're really meant to be easy problems. Like, okay, here's a couple points, just reward you for studying hard. So let's build up to something more meaningful then. A little bit more challenging of a problem. Like problem number 52. Whoa. Now that's a problem. So it's square root of 2 minus 3i, square root of 3 minus I, square root of 3 minus I. And the good news for me is I'm going to sit back and relax while you guys multiply this out. It should easily take us the rest of the hour. Go ahead. All right, I'm kidding. Right. All right, you guys are a little bit weary from your test. I get it. There is a shortcut here. It's called DeMoivre's theorem. Yeah, I wouldn't want you to actually do that. That would be awful. I would refuse to do that. I'd be like, no way. It'd be really difficult not to make a mistake along the way and end up way far away from the correct answer. But there is a shortcut. Like I said, it's called DeMoivre's theorem. And I'll just write it down here, or I'll show you here, that when you have something in polar form and you want to raise it to the nth power, then you're just going to take the radii and raise it to the nth power. What happens with our angle theta? It gets multiplied by n, right? It's not to the nth power, it gets multiplied by n. So I guess the first thing to do for us is to figure out what this looks like in polar form. So I'm sorry I don't have this one graph for us already. Let's think about this. If z equals the square root of 3 minus I, there's your real part, there's your imaginary part. What's the coefficient of my imaginary part here? -1. So let's draw ourselves a little triangle here. What quadrant should I draw my triangle in? Does anyone know? Andre? Not with a negative I. That would be below the x-axis. Oh, are you drawing it in the air? Okay. All right. All right. Fourth quadrant. Thank you. So, fourth quadrant. Let's see. So, this side is going to have length square root of 3. This side is going to have length 1. When you draw your triangles, make sure that the hypotenuse is connected to the x-axis. We never connect it to the y-axis. There's two things I need to know. I need to know theta, and I need to know r. Start with r. Tau. How should I find r? Pythagorean theorem, right? R is just going to be the square root of negative 1 squared plus square root of 3 squared square root of that gives me 2. Okay. How are you going to find theta? You got lots of choices. You could use inverse sine, inverse cosine, inverse tangent. What's going to work though for you? Yeah, I'd go with the one that makes it easiest, right? So this is a negative 1 here. So the ratio of these two sides, the negative 1 and the 2, that goes along with which trigonometric function? Which trigonometric function involves my angle, this side, and the hypotenuse? Sine. So let's see. Sine of theta equals negative 1/2. Inverse, or theta equals the inverse sine of negative 1/2. And that gives you negative 30 degrees off your calculator. Is that the angle I want? No. Brandon, what angle do I want? Perfect. 330 degrees. I want this angle here. Okay, thank you, sir. Let's see. Let's rewrite this now in polar form. So that's going to be 2 times the cosine of 330 plus I times the sine of 330, like that. That's looking good. Let's raise that to the 6th power. So I'm going to take 2 cosine of 330 plus I times the sine of 330 and raise that whole thing to the 6th power. And what that gives me is 2 to the 6th power times cosine of 6 times 330. Oops. Plus I times the sine of that same angle. 6 times 330. Let's clean this up. 2 to the 6th power is 64. And that's going to be the cosine of, I think, 1980. Plus I times the sine of, again, 1980. Now, in a problem like this, I'm going to ask you to go all the way back down to the form of A plus BI. That is, I don't want it in polar form anymore. That's not what we started out in. That's not what we're going to end up in. Let me pause for a moment. We okay right here? No, 64. 2 to the 6th power is 64. Yeah. Okay. This, I'm thinking, is more than once around the unit circle, right? So let's figure out what angle it actually is. And here's what I would suggest. Let's take 1980 and divide it by 360. You get 5.5. So what this is saying is that that angle is really 5 times around the unit circle and then a little bit more. So if I subtract off the 5 and times by 360, I find, oh, that's really 5.5 times around, or it's really equivalent to a 180-degree angle. So let me rewrite it like this. 64 cosine of 180 plus I times the sine of 180. And that's looking better. But let's see here. These look like pretty friendly angles. What's a cosine of 180? -1. What's the sine of 180? And if I distribute this, just -64, right? Wow. That's not bad. -64. Are we good with that? Good with that angle? Yes. Yeah, you need to put it in polar form first. Yeah, your alternative to put it in polar form is to do what I was kind of teasing you about in the first place, and that is multiply it by itself 6 times. And even for myself, I'd make a mistake if I had to do that. Yeah. First step is to draw your triangle and put it in polar form. Yes, absolutely. Yep. Anything else? Is there a way to check it? 0i. Right, because sine of 180 is 0. So 0 times I, well, it's just 0. So when I distributed the 64, I just left it off. You could, with your answer, write -64 plus 0i, but I probably wouldn't bother with the 0i myself. There's nothing wrong with it, though. Let's check this out, though. You can actually double-check your work on your calculator. But here's the deal. I'm going to show you how to double-check your work. You still have to show me the work, though. All right? So you can know before you hand it in, you got this right. Let's see. Square root, I need this in parentheses, square root of 3, hit the right arrow to exit the parenthesis, minus I. Does anyone remember where I is on their calculator? Yeah, okay, that's what I thought. It's right above the decimal. So what do I have to do to get to I? Second decimal. So square root of 3 minus I want to right parenthesis, and I want to raise that to the 6th power. Bada boom, bada bing. Yeah, way to go. Thank you. All right, cool. Beautiful, beautiful, beautiful. My favorite class. Don't forget to tip your servers. I'll be here all week. Okay, so -64. Looking good there. How about if we had to reverse this? What if I had something like this and I needed to find the 6th root or something else and I wanted to find a cube root? Well, that's where we're going to use another theorem for complex roots. And that's on the back of your handout. Basically, this is really undoing what DeMoivre's theorem is doing. If you're trying to find something raised to the nth power, then you're going to raise the radius to the nth power. You're going to multiply the angle by n. Okay, so let's think about the opposites here. Something raised to the nth power, the opposite would be something raised to the 1 over nth power, which is what you have here, the nth root of the radius. And instead of multiplying here, what's the opposite of multiplication? Division. So you're going to take your angle and divide it by theta. The only catch is, and we'll work with this in degrees first, is in addition to taking your angle divided by n, you're going to take 360k divided by n, and k is going to have values from 0, 1, 2, all the way up to n minus 1. N is the degree of your root. Wow, a lot going on here. So, let me help out with an example, maybe two, depending on how much patience I can ask from you. All right. I didn't point here, but that one's okay too. Let's start out with negative 8. In order to find the three complex roots of negative 8, one thing that you're going to do, see, we're on z equals negative 8. I want the cube root of z, or the cube root of negative 8. So the first thing I'm going to do is I'm going to rewrite that as a complex number in polar form. Negative 8 we'll think of as negative 8 plus 0i. Let's graph it in rectangular coordinates first, and then try and figure out what's going on in polar coordinates. Where is this point going to be on my graph? You got your real and your imaginary. It's going to be right on the real axis, right? It's going to be here at negative 8. There's two things that I need to know. One is I need to know r, and the other one is I need to know theta. Can anyone figure out what theta is in degrees? Yeah, thank you. 180 degrees. Can anyone figure out what r is? How far is that distance? Positive 8. So there you go. There's r and theta. So that theta comes down here. And I'll write it in both spots. And I'm putting in that formula that I've written above. This one right here. Theta is 180. N is 3 because I'm trying to find the cube roots. And I get this. K goes to 0, 1, 2, and that's n minus 1. So that's it. You're going to have 1, 2, 3 different complex roots of this number. Let's keep going. Let's simplify this. What's the cube root of 8? 2. Times the cosine of 60 plus 360 divided by 3 is 120 times k. And for the second part of this, you can just copy this angle again. It's I times the sine of 60 plus 120k. And again, that's k equals 0, 1, and 2. So it's just filling in a formula, albeit an ugly formula, a useful formula nonetheless. So that's z sub k. Now that we've simplified this general formula, we've got to go back and figure out what it looks like in particular cases. So let's start out with k equals 0. So z sub 0 is going to be 2 times the cosine of 60 plus 0 times 120. Well, 0 times 120 is just 0. So it's a cosine of 60 plus I times the sine of that same angle. These angles always have to match. Let's leave that there for a minute. Let's go up to z sub 1. Again, it's going to be 2 times the cosine. Cosine of what? Let's figure it out in this case. So if I put in a 1 here for k, what angle am I going to get? 180. So cosine of 180 plus I times the sine of 180. And again, for the moment, I'm just going to leave it there. Finally, z sub 2. If I put in a 2 here, 2 times 120 is 240 plus 60 gives me a cosine of 300. plus I times the sine of 300. Now we can clean these up, and quite often on an exam I'll ask you to clean up, at least one. Let's start with the middle one. What's the cosine of 180? -1. What's the sine of 180? So this is -2 times 1 plus 0i, or better yet, just -2. And that makes sense. That's the answer that most of us could come up with, right? The cube root of -8 is -2. That's the one we could easily get. The one that'd be a little harder, or the ones that'd be a little harder, are these two. This is going to be 2 times 1/2 plus I times, square root of 3 over 2. And when I distribute that, I get 1 plus I times the square root of 3. I normally like to write the I behind this, but the problem is if you wrote the I behind it, sometimes people get sloppy and they'll take the square root of 3i, which is way wrong. So let's just be careful and put the I out in front here. Likewise down here, that's going to be 2 times 1/2 minus the square root of 3 over 2 times I, which is going to be 1 minus I square root of 3. When you distribute that, the 2's cancel out from the denominator. So there you have it. 1, 2, 3 cube roots of -8. Whew. Want another one? Vivek, question, yes. Yes. So if this was a fourth root here, then k would go from 0 to 3, and I'd have another one of these down here. Absolutely. But this is the way you have to proceed on these things. You have to first put your number in polar form, and then use this formula in one of two forms. Notice I've given you this formula in degrees and in radians. So this one's in radians. This was that formula in degrees. Any other thoughts on that one? Nothing. I want to go home. All right. So let me give you some homework. Tell you what, I don't want to give you homework, so let me just give you some suggestions then, right? 15 through 21, 25 through 31, 35 through 37, and 43 through 59. Have fun. See you. Yay, thank you.